Mayan ruins are hidden throughout the Central American jungle, and archaeologists are eager to find these relics of a fascinating civilization. Unfortunately, they often find that the most effective way to discover these magnificent buildings is by contracting expensive aerial Lidar platforms, which many archaeologists cannot afford. Our goal is to make cheap, autonomous aerial Lidar platforms a reality by developing a path planning algorithm that will increase the effectiveness of these platforms. What are the requirements of a LiDAR surveying path? A crucial point is that we need to avoid obstacles such as trees or mountains, but that is not enough. For example, we can't just fly at a constant altitude like the quadcopter in this video. Our task is when given a set of waypoints, we return a list of waypoints that consistently keep the ground within the LiDAR sensor's range. This will allow us to get accurate survey data. Take this path, for example. It clearly ascends and descends while following some hill. When we render it using a 3D model of the region, we can see that it does in fact correctly follow the hill. For more detail, let's take a look at this profile view in a graph. Basically, this graph is just the same angle we saw in the 3D model, but put into 2D. The x-axis is the distance along the path, while the y-axis represents altitude. The red line is the surface of the hill, while the blue line is the path. If we look closely, we can see that our path mirrors the surface of the hill exactly. This is because this path was generated by finding every single point along our path where the altitude changed, and then adjusting our altitude accordingly. Let's get an idea of how well this stays within the LiDAR sensor's range by shading the region that we expect the LiDAR to reach. As we can see, the shaded region is the entire region between the surface of the hill and our path. By adjusting our altitude every single time the hill changed altitude, we have created the ideal surveying path. In practice, this ideal path is not as great as it may seem. The path involves 340 different waypoints tightly packed together, and the quadcopter is physically unable to hit them all with precision. As a result, its flight is very unsteady, and it does not do a good job of following the path. Again, let's look at the 3D rendering of the flown path. We can see that the quadcopter was jumping around quite a bit as it went through its path, indicating that it was unable to correctly follow it. Our next step is to find a way to transform our ideal path into a path that is easy to fly, remains crash-free, and also minimizes the loss of LiDAR precision. One of our simpler smoothing algorithms finds the maximum altitude over 20-foot intervals and then sets the altitude to be the maximum over the interval. On this graph, it is graphed in yellow, and our original ideal path is graphed in blue. As we can see, this new path is quite a bit smoother and reduces the waypoint count from 340 in the ideal path all the way down to 40. However, when we shade the area between these two paths, we can see that this area is pretty large, which indicates that we are probably sacrificing a decent amount of LiDAR penetration with this smooth path. When we graph our path in profile view and compare it to the hill's surface, we can clearly see some of the areas where it is out of LiDAR range. Because the path takes a maximum altitude over a certain interval, it tends to start its descent further away from the surface and then falls out of LiDAR range while descending. So is the trade-off of smoothness versus LiDAR penetration worth it? When we flew the smooth path, we found that the quadcopter was easily able to maintain a consistent path and fly smoothly. For example, in this section of the path, we did not see any of the quick plateauing movements that we saw when we flew the ideal path. In fact, the quadcopter is able to descend down the hill and then ascend back up the hill without any trouble. When we look at the flown path in the 3D viewer, it is the yellow path in this case, we can see that it is altogether much smoother than the ideal path's flight was, while also being a massive improvement over the constant altitude blue path. While the ideal path may still fly closer to the ground, the fact that its flight is so unreliable is troublesome, as the guarantees of the ideal path are meaningless if the quadcopter cannot actually fly the path. In conclusion, we have developed a path planning algorithm for LiDAR surveying as well as a toolset to analyze different ways to simplify a complicated path. In the future, we hope our work can be used to analyze paths with stronger mathematical guarantees of correctness and improve the cost-effectiveness of aerial LiDAR platforms for archaeologists.